Hello, statistics. Let's get into section 9.4, testing the difference between proportions. So a researcher might ask a question like, if you've ever been to Olive Garden, right, you have a choice. Is there a difference between the proportions, remember, slash percentages of customers who order salad or those who get soup? Is there a difference? Or is there a difference in the proportion of men who exercise regularly? Is that less than the proportion of women who exercise regularly? So we're testing a proportion. Remember, we're back to that binomial situation. Either you order salad or soup. Either you exercise or you don't. There's no in between. So our hypotheses are going to look similar, except of course, since we're using proportions or percentages, we use P instead of mu. I don't really love this second column because I think that you're intelligent enough to figure out what we're doing over here. So our H sub O, like always, is always our hypothesis with equality. So H sub O will always be proportion 1 equals proportion 2. If it's two-tailed, those things are not equal. Is there a difference between them? If it's left-tailed, we're looking is proportion 1 less than proportion 2? And right-tailed, our H sub 1 will be proportion 1 is greater than proportion 2. If we were looking at these in terms of their relation to 0, remember, if you subtract them, if they're equal, they would not be equal to 0. If it's left-tailed, proportion 1 minus proportion 2 would be less than 0. And if it's right-tailed, our proportion 1 minus proportion 2 would be greater than 0. I like the left-hand column better. I think that you all understand that a lot better. So let's talk about a lot of side work. The one difference between this and our testing for the difference between means is there's a lot of side work. So we've got a p-bar that we've got to deal with. P-bar is the weighted estimate based on our H sub O, and H sub O says that they're equal. There's a calculation for p-bars. Ignore this middle bit. Just jot down that p-bar is equal to x sub 1 plus x sub 2 all over n sub 1 plus n sub 2. Our standard error of the difference, this is our margin of error. Again, I'm not sure why I got so crazy with this. Our standard error, or margin of error, sigma of p hat 1 minus p hat 2 is equal to, this one's worth writing down. Hopefully you can see it. Let me make it bigger for you for a second. Because this is going to pop around when we do a confidence interval and the denominator of our test value. So it is the square root of p bar times q bar times 1 over the sample size 1 plus 1 over the sample size 2. It looks messy. We got some side calculations. The reason I had to mention p-bar was because it shows up in our margin of error. It shows up in our test statistic. It shows up in our confidence interval. So let's do a quick little thing here. So p hat at 1 and p hat 2. We know those, right? P hat 1 is the proportion or the percentage of population 1. So x sub 1 over n sub 1. P hat 2, we've always just dealt with 1, but we've got 2 different samples we're dealing with, is the number of items with that characteristic over the sample size in sample 2. What is that? Oh, x1 and x2 is equal to our number of units that actually possess that characteristic. So that's where those numerators come from. If 15 people out of 45 order salad, it would be 15 over 45. Here we've got, these got crowded together. We know that N1 and N sub 2 are our sample sizes for each one of our 2 samples. P1 and P2 are our population proportions. That's what in our hypothesis we're saying that those 2 things are equal. I'll put hypothesis here. So Q sub 1, right? If P sub 1 is 28% of the population order soup, Q sub 1 then would be the complement of that, 1 minus P1. Q2 is the complement of our second, whatever it might be. 52% of women exercise regularly, so 48% of men. And we know that Q bar is equal to 1 minus P bar. We always know that any kind of P and any kind of Q add up to 1. So use the complement of those things. We're going to calculate some stuff over here on the side, including P bar. Because remember, P bar shows up in this formula right there. So let me put this up here and then we can talk. So here's our Z test value or our test statistic. This is what we use to compare to our critical value so that we know if we're going to reject or not reject. So P hat 1 minus P hat 2. So remember, those are our two proportions from our two independent samples. Subtract P1 minus P2, but remember, according to our hypothesis, these guys are equal, so these guys will be equal to 0. In our denominator, we've got a giant square root of P bar times Q bar. We got to do some calculating to find our bars, times 1 over n sub 1 plus 1 over n sub 2. It looks messy. Don't worry, we're going to do some calculations down the side to make sure that you've got this. First, let's talk about our assumptions that we have to make. Nobody likes making assumptions in math, but we have to, in order to do our z-test for our two proportions, we must know that our samples are random, that they are independent, and back to that binomial situation, n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Hopefully that sounds a little familiar. So we are going to follow the same 5-step hypothesis testing procedure. We've been doing this for years now, right? 5-step hypothesis test, nothing has changed, except we're going to do a little side work. We're going to find p hat of sample 1. We're going to find p hat of sample 2. We're going to find p bar, and we're going to find q bar. We have to do those side problems before we can do anything else in the problem because those are required in our formulas. Right, so we'll get these straight, no worries. I actually do them before I start doing anything else. I'm going to jot them down on the side because then I never have to think about them again. All right, so we've got a seatbelt use an example. In a random sample of 200 men, 130 said they use seatbelts. In a random sample of 300 women, 63 said they use seatbelts. Test the claim that men are more likely to use a seatbelt than women at the alpha equals 0.01 level. Show the traditional and the p-value methods. Let's worry about that after. So let's do a couple of things here first. It looks to me like men are going to be sample 1, right? So population 1 is going to be men. Population 2 is going to be women. The only reason I chose it that way was that's because it was how it was written. So I just said on that last screen, we got to calculate some stuff. So let's start by calculating our p hat 1. So this is our population, this is our proportion, our sample proportion for men. So let's see, there were 130, that would be x sub 1 out of our sample size 1. So 130 out of 200 is going to be something like a 0.65. Then I'm going to do the same thing. I'm going to find my p hat for sample 2. Sample 2 is women. So there were 300 women. So that's my n sub 2, second sample size. 63 used seatbelts. So 63 out of 300 is going to be something like, what, 0.21? So I've got my p hat 1 and my p hat 2. The second thing I need to find is p bar. So we set in that formula box that P bar was equal to the sum of my x's over the sum of my sample sizes. So the two x's, and I just look at this little side work right here because my two x's, my x sub 1 and my x sub 2, are 130 plus 63 over the sum of my samples, so sample sizes, so 200 plus 300. Let me scooch that over a little. So this is what we're using as then our kind of our population estimate. So that's going to be something like, I don't even have that number written down. I'm going to go, remember for population proportions or just calculating these, I'm always going to go to 3 numbers after the decimal. So 193 divided by, let me clear that out, 193 divided by 500. Sorry, my calculator's not cooperating. That's going to be something like 0.386. 0.386, which means Q bar, remember, is 1 minus that, so that's going to be something like 0.614. All right, side work is done. Mark that off. We're just going to need to refer to that. So let's go to our hypotheses. So step 1, H sub O and H sub 1 in our claim. Well, H sub 1, we're saying that the two population independent sample proportions are the same. In the H sub 1, it says men are more likely to use a seatbelt. Well, population 1 is men. So if they're more likely, they'd be greater than. And that was what our claim was. Step 2, I'm going to just go with the traditional method here. When we do a z-test, when we've got population proportions, notice that our critical or our test statistic was z equals. So you're going to your z table. This is a right-tailed test, so you only need to use alpha equals 0.01. So our critical value is going to be right-tailed will be positive 2.33. So z table for this one. Step 3, this one probably needs more space than what I left. So z is equal to, I know in the numerator I do p hat 1 minus p hat 2. So p hat 1 we calculated at 0.65 minus p hat 2 is 0.21 minus that 0, because remember, if they're equal, they subtract and become a 0. In the denominator, I've got myself a nice giant square root, and it's going to be p bar times q bar. Well, p bar was 0.386, q bar was 0.614, times 1 over the first sample size, 200, plus 1 over the second sample size, 300. Remember, that is not 1 over 500 because you'd have to have a common denominator. That's why we let the calculator do the work for you. I would personally hit pause right here and do the calculations and make sure that you get the same very large number. I didn't plan this one out very nicely. I ended up with a z value of somewhere around 9.90. Super high test statistic. If we're thinking about a 2.33 as our right-tailed critical value, 2.33, and I've got a 9.90 way out here, obviously that's going to be in the reject H sub O region. So if I reject H sub O, that means I don't think that the proportions are equal. That means there is enough evidence to support the claim that men are more likely to use a seatbelt than women. And there we've got ourselves a hypothesis test. The hardest part about this is all the side work and keeping everything straight. We'll go through examples. By the way, if we were going to do a p-value test and we went to the z table, so z of 9.90, that's greater than 3.49, I believe it was, which means that we use a 0.9999. It's right-tailed, so I have to do 1 minus, so that'd be 0.0001 is what I would use for my p-value. And if I compare my p to my alpha, 0.0001 compared to 0.01, my p-value is definitely less than alpha, which means to reject H sub O. So if you do like that p-value method, please use that. One last thing, let's look at the confidence interval. Don't be intimidated by this confidence interval. Hopefully you figured this out at this point. So in the middle is always going to be our P1 minus P2. That yellow really covers it up. Let me try a different color. And then we've got our inequalities, right? So the only difference between these two sides is it's going to be our p hats, the difference of our p hats plus and minus our z critical value times that square root of, this is lovely, make sure you get it written down, p bar 1 times q bar 1 over the sample size of sample 1 plus p hat 2 times q hat 2 over the sample size of the second sample. Again, the math is the calculator math is the hardest part of this. We'll do some examples together and some work together in class, make sure everybody's got the calculator figured out, and that should be it for section 9.4. Thanks for hanging around. Come back with any questions, any calculator work. Let's make sure we've got this. Lots to keep track of as far as P's, Q's, P hats, Q hats, P bars, Q bars. So watch out for those. They get a little tricky. Refer to your notes, refer to your examples. Have a good one. I'll see you next time.